Hello, everyone. Welcome to ECE 5307. Sorry that we have to do our first lecture online. Hopefully, everybody can see my the screen that I'm sharing. Can you guys give me like a thumbs up to make sure everything's okay? Awesome. Okay, so what I'm going to do today is I'm going to go through two sets of slides. One is more or less summary of what's on the syllabus, just how the course is going to be organized. And then the second set of slides is going to be sort of an introduction to the kinds of things we'll be talking about technically in the course. If you have a question, feel free to post it to the chat or even just unmute yourself and ask the question. So, let's see. So starting with instructional team. So this is me, Professor Phil Schneider. I'm going to be holding office hours in my office 3616 simultaneously on Zoom Thursday mornings from 10 to noon. And then the TA Sarav, who's going to be grading the labs, he's going to have a variety of office hours, but they're going to be Zoom only. He's going to have some Wednesday afternoon, Thursday evening, and Friday morning. By the way, everything on these slides and on all other slides that is colored green, they're all hyperlinks. So you can click on them. And a lot of times I'll have, links to additional things for more explanation. Okay, so at a high level, our objectives in this course is to understand what machine learning is. We're going to be focusing on several tasks from machine learning, regression, classification, clustering, dimensionality reduction. And in that sense, we want to learn both or understand both the mathematics as well as standard coding tools. So for the mathematics, that's the math behind models, algorithms, various methods. We're going to have to be using concepts from linear algebra, from probability and statistics. And then in terms of coding tools, I won't assume that you have any experience with these things, but you'll be learning Python and then some packages within Python like NumPy, scikit-learn, Jupyter, Matplotlib, PyTorch. And then we'll be using GitHub to distribute and collect materials, as I'll describe in a moment. So prerequisites, if you're an undergrad, you need to be an ECE. If you're a grad student, you can come from any major. I'm going to assume that you guys have basic calculus and linear algebra. If you're an ECE undergrad, that would be like things in those courses: vectors, matrices, eigenvectors, partial derivatives, gradients, things like that. The first lecture will be a review of some of that material, as will homework one. And we'll also need probability and statistics, again, at the undergraduate level. So things like these courses at OSU, basic concepts like mean variance, correlation, covariance, expectations, PMFs, and so on. And we're going to be reviewing that material when we need. And then also some basic scientific programming, such as C, C++, MATLAB, or Python. And we will be using Python, but again, I don't assume that you know Python already. You'll just learn it in this course if you don't already know it. So except for exceptions like today, we're going to be lecturing in Scott Lab E004, 410 to 505 every Monday, Wednesday, Friday. I'm going to be checking attendance randomly by calling you guys out by name and asking you questions. I'm going to post lecture PDFs like this one in advance. And I strongly suggest that you download those lecture PDFs either in hard copy or to some device. I'm going to basically have blanks in the lectures for you to fill in. And that's because I find that if the lecture is completely passive, it's very easy for you guys to zone out and stop paying attention. So just by having some things to do, it really helps. Also, you should be, there's things I'm going to say that are not directly in the notes that I suggest you write in the margins as well, things that you find significant, but that are not explicitly in the notes. And if we have other cases like today where we can't lecture in person, then we'll do it via Zoom. I already talked about the office hours. And one way of answering questions in this course, I'm going to be using Carmen discussions quite heavily. So if you have a question on a lab or on lecture material or something, there is already created in Carmen various discussion posts that you can just enter your question in and then get a response. And the response could come from me, it could come from the TA, but it could also come from you guys, like especially if a student has a very specific issue with the lab that they're seeing, maybe they're using some kind of software and some other student may have already encountered exactly that really weird issue and may already know the answer to the question, whereas like myself or the lab TA may have never seen that issue. And we might be slower in responding than all of you. So I do encourage you guys to post answers if you feel like you know them to the questions that are being asked by your peers. In terms of grading, there's a number of components in this course. There's going to be weekly coding labs. They're typically going to be due Fridays midnight. I think in all cases they will. And they're going to count for 20% of your grade. Then we're going to have weekly Carmen quizzes, almost always Fridays at 4 p.m., although there are a couple exceptions, like the very first quiz is actually next Wednesday in 9 days from now at 4 p.m. Those will be worth 20% of your grade in total. There's going to be 3 midterms this semester. They're going to be increasing percentages. The first one, 5%, the next 10, the third, 15%. The first midterm is just going to be actually like a 25-minute midterm given on Friday the 17th. And that is going to cover the linear algebra prerequisite. I'm going to spend a lecture on it, but it is stuff you guys are already assumed to know. So, and as you can see, the percentages increase. So like if you bomb the first midterm, maybe you need to adjust to how this course is, structured and graded and all that, then it's not that big of a deal. It's only worth 5 points or 5%. There's going to be a final project worth 25% at the end of the term. Talk about that separately. And 5% will be for attendance and participation, like I mentioned earlier. I'll just be calling on you guys randomly. Okay, there's going to be homework posted this term, as well as solutions, but I'm not going to grade it. I wasn't able to find a grader this term, so you guys are going to be responsible for doing the homework on your own and for motivating yourself. I'll say this much: if you just don't do the homework, you'll probably fail the exams. So keep that in mind. The homework is not really meant to be optional. It's meant for you guys to do. It's probably the main way that you'll learn the material. And so if you don't do it, you'll probably be pretty lost. Okay. In terms of the final letter grade, I'm going to curve things, and it's going to be based on the cumulative score that you earn throughout all these components at the end of the quarter. Undergrads and grads are going to be graded differently, and this is how I'm going to do the grading. So for the undergrads, the top third of the undergrads will get A's, and in particular, the 33.3 percentile will give the lower boundary for the A minuses. Then the middle thirds of the undergrads will get, these forms of B's, and so then the bottom 33.3 percentile will give the B minus boundary, and then anyone that's in the bottom third below that, you could get any score, possibly even a failure. So that's how I'm going to be doing the grading. And if at some point, in the middle of the semester, you have a question about how you're doing, you can just let me know, and I can see, where you are. I will be posting some histograms so you can see that information hopefully directly. For the grad students, the top quarter will get A's. The second quartile, A minuses. So that means in total, the top half of the class will get A's and A minuses. And then in all these cases, all the other boundaries between all these different letter grades will be uniform. So, once I set two boundaries, and all the other boundaries are determined. So for grad students, you guys should be doing B or better. Otherwise, you're in danger of, having your grade point average go below the what is it called? The level at which you're making good in good academic standing. And it is definitely possible in this course to get lower than a B. It's possible to fail as a grad student, in fact. So it's really going to be up to you. If you're performing much, much worse than your peers, you're going to get a really bad grade. So keep all that in mind. So in terms of the final project, the goal will be to apply the machine learning concepts that you're taught in this class to a data set that I'm going to give you and a design objective. And there will be an in-class Kaggle competition where you guys will compete against each other. And I've found that really helps to motivate students. The projects are going to be team-based with three-person teams. However, if you prefer to work alone, really you can do your part of the team project yourself, and then all you have to do at the very end is merge your 5 pages of the report with your teammates. So you can do this with minimal interaction if you want. On the other hand, if you have people that you want to work with, you guys can work together. And usually, you can do better than individuals if you work together. So this is really up to you how you do the project. And the deliverables of the project will be the Python code that you write, a written report that will be posted in PDF form on Carmen, as well as the Kaggle score that you get. And we'll talk in detail about this later in the term. There's no assigned textbook for the course, but these are the 3 that I think are best if you're looking for optional textbooks. The first one is a textbook that's coming a bit more from the stats perspective. It's really good for theory. It's free. This middle textbook here is a paperback. It's really not very expensive, but it has a good blend between concepts and Python coding. And then this last one here is also free. It's quite a bit more extensive. The focus is more on deep learning than on classical machine learning, and has a good blend between concepts and coding examples in a number of different frameworks, although we'll be focusing on PyTorch. So again, those are just all optional. And in my notes, which are what I'll be really following closely, there are links to many things. So sometimes, if you have a question on a particular concept in the course, there'll be a link and you can go to a Wikipedia page if that's what I recommend or whatever it happens to be. Okay, there's a question about the grading. Can your grade get curved down? I don't really know what that means. The grade boundaries, so the way the grading works is you get grades on all these things, you get an average score, and then maybe it's a number like 80, 82. Then you look at where that score falls with regard to these different grade boundaries. So there's no up or down, it's just where your score fits relative to the boundaries. I don't know if that answers the question.
Kind of. I was kind of thinking more if like you have 93% total, that could curve down to a B if that falls below the where it would stand on the curve.
93% means nothing in this course. What I mean is I don't know if you're thinking about a different course where 93% meant something. But I'm saying in this course, 93% doesn't really mean anything. It's really just about how everyone scores on these things. And then there's sort of a histogram. That histogram gets carved up according to these rules. And that's
Okay.
how it goes, if that makes sense.
Yeah, that makes sense. Thank you.
Okay. So we talked about those things. And so we'll be using Carmen Canvas as typical at OSU for a lot of things, but not for everything. So here's sort of a list of a number of things we'll be using it for. Let me just sort of emphasize announcements. I'll be posting important announcements on Carbon Canvas. Make sure your notifications are enabled. Also discussion boards. So again, like, on a particular lab, someone will post a question in the discussion boards that then there'll be an answer that might be super useful to you, but you have to make sure that you are subscribed to the discussions. Otherwise, all this is going on without you really knowing. But if you are subscribed, then you'll get to see when these questions are answered, and that might really help you if you encounter some of the same issues in the labs. Yeah, homework and solutions will also be posted to Carmen. You'll find links to the labs on Carmen. I'll describe how we're going to use GitHub in just a moment. You'll find the quizzes. The quizzes in this course are you're going to be short, 7 minutes, 5 multiple choice questions on Carmen. Exams, you'll find solutions, histograms, final projects, you'll find instructions and so on. And of course, your grades will be posted there as well. Okay, so GitHub, I'm not sure how many of you guys have worked with GitHub, but GitHub is the main way that people in the machine learning world and as well as software world share code. And it's also very useful as a version control system if you're writing code and you want to sort of say, here is like a really solid version of my code. I'm going to sort of save that version, and then I'm going to maybe make some modifications to that. But if something goes massively wrong, I can always come back to where I was when I saved that last working version. So we're going to use GitHub to post the lecture PDFs. You'll also find demonstration code posted there. These are going to be in the form of Jupyter notebooks, which I'll describe in a moment. This is where you're going to find. Okay, so the way the labs are going to work is that you're going to find a link on Carmen. You're going to click on that link, and it's going to bring you to. It's actually going to create what's called a repository for you on GitHub. And a repository is like a little location in the internet that there may be some starter code put there, and then you're going to bring that down to your local machine, or you're going to work on it in the cloud. And you're going to be basically filling in some blanks in what's called the Jupyter notebook. And then once you're happy with it, or as many times as you want, you can basically save or commit a copy, which pushes it back up to the cloud. And eventually, after the deadline passes and the grader is going to grade your lab, he's going to take that information from the cloud, bring it down to his local machine where he can run your code and see what it looks like. So we're going to be using GitHub for that. The final project will be handled very similarly to the labs. Now for the lecture PDFs and demo codes and stuff like this, there's going to be this primary course repository. So this is a private repository, but you can get access just by following the instructions in one of the Carmen Canvas announcements that I posted in the weekend. Once you get access, you'll be able to click on this link and you'll be able to see what's there. There's going to be a bunch of information, but including the lecture PDFs and the demo code. And you can view PDFs directly within GitHub in a web browser. It's not super convenient because in my experience, it lets you view the first pages, and then after that, it takes a while to load the remainder of the pages. So what I recommend is to actually pull those PDFs and Jupyter notebooks down to your local machine where you can get direct access to them and even import them into a note-taking program like GoodNotes or Notability. And from there, you can edit the PDF and so on and take your notes. So that's what I recommend. And in terms of running code and doing the labs, there's basically two ways to do it. One way is to work in the cloud using Google Colab. So in this course, the labs that we run are not going to be very computationally demanding. Google Colab gives you a certain amount of free computing resource, and that is definitely sufficient for what we're going to do in this course. Um, Another option is for you to clone the repository to your local machine, your laptop, or whatever, and then install the required Python tools in your laptop and just run things locally. That's what I do. That's my preference, but some of you guys might also enjoy using Google Colab. Yeah, and this is sort of what I said. You basically pull down this code skeleton from GitHub, you modify it, and push it back up to GitHub where the TA can access it for grading. Okay. As I mentioned before, we're going to be using Python. It's a general and powerful language, but the main reasons we're using it is that it's the main way that people are doing machine learning these days. There's tons of libraries there, especially for deep learning, and it's free and open source. So again, no Python background is assumed. We'll teach you, but you do need to start with something similar like C or MATLAB, and from there it's pretty easy to learn Python because it's really similar, just some differences in the details. Also, we'll be using object-oriented programming ideas, so having some background in that is also important. There are in the main course repository, there are various tutorials on using Python and NumPy, and as well as practice materials. The practice materials are totally optional, but they're there if you want them. I mentioned that we'll be using Jupyter notebooks for the demos and the labs. And this is sort of what a screenshot of a Jupyter demo looks like. You can see there's a mixture of text, hyperlinks, little code blocks, as well as outputs from those code blocks. The outputs could be text, they could be plots. So you'll be sort of filling in blanks like this in the labs, and then the TA will be looking at what you do. Okay, so with all that, just sort of a few high level warnings. This is not an easy course. There's lots of linear algebra, lots of probability. There's a lot of deliverables. There's labs and quizzes every week. There's 3 exams. There's a final project. There's also this weekly homework, which even though it's not graded, it's not meant to be optional. It will take some self-discipline to do it. So, that makes the course itself pretty tough. Also, the linear algebra component of the course is what most students find the most challenging. It is really the language that we're going to use to teach machine learning. So if you can't speak the linear algebra, it's very hard to understand what we're talking about. It's the main reason students drop the course and do poorly on exams. So it's really, really important to invest some time at the beginning of the term to brush up on this material that I'm sure you learned it at some point. Maybe it was a while ago, or maybe you feel like you never learned it very well the first time around. Now is the time to learn it. So the first lecture, I'll review some of the things we're going to be using. There's going to be a homework and a quiz that you can get some practice with. And then there's going to be the first exam, which is like, as I said, a half of a lecture, 25-minute exam, which is going to, just provide further motivation to really learn these concepts. In terms of the lectures, I strongly recommend taking an active approach, meaning don't just sit there zoning out, looking at your iPhones or whatever. Really, really listen and especially ask questions. Usually when one of you guys has a question, many other people have the same question. And so it's really useful for you to ask it. It helps the class as a whole a lot. So don't be shy. Make sure to ask questions. And then finally, don't cheat. Don't copy from other people on the exams, on the labs. I'm obligated to report cheaters to the Committee on Academic Misconduct. So just to let you know. So this is a good time to stop. for questions. Does anybody have questions on anything I've covered so far? No questions. Okay. It's a bit surprising. All right.
Actually, I have a question. Sorry. So for the exams, how will those be conducted?
So the exams are going to be given in the lecture room. Um,
Hmm.
so the
But
very
like
first
pen and
exam,
paper,
yeah, pen and paper, right. The very first
or
exam will
okay.
be be the second half of the lecture period, and then the other exams will be the full lecture period. For the first exam, you will not be able to bring in any materials, like you won't be able to use any kind of calculator. You won't need a calculator or anything like that, or your phones. Um, you will you won't also be allowed to use a note sheet. But for the other exams, I'll let you bring in a page of handwritten notes. Um, and the main objective there is actually making that note sheet is a super important exercise, going through all the lecture material when you're done learning everything and just summarizing it to yourself and making sure you understand, each individual thing and writing it down as needed. That's a super useful approach to studying. Okay. So, will I have study guides for exams? No, I think it's counterproductive for me to do a study guide for exams, because then I think students feel like they don't really have to study themselves. I think going through the process of, going through everything, every line and every lecture is really what I recommend in studying for the exams, not just looking at some summary that I give you. An earlier question, what's the best place to find information or brush up on linear algebra? So that stuff has been posted already to the GitHub main GitHub page. So I have some lecture slides. It's called lecture 1. And so you can yeah. So, linear algebra it's a deep subject. I'm not expecting you guys to know everything about linear algebra, or certainly not expecting you guys to be experts on everything from linear algebra, but I do need you to know the very basics quite well. And so I have summarized those basics in just a few pages of lecture notes that we can cover in one lecture. Um, so that's what you can find on the course, the main repo. Will there be a schedule to complete the homeworks? Yes. Definitely the homeworks will be posted regularly on Carmen, so you'll see it pop up. Typically, the homeworks will be released typically on a Friday when we're finished covering that unit of the course. And then they'll be due maybe the next Friday or 2 Fridays later, depending on how long that unit is. Okay. Will it be a sample question for the exam? Yeah, I'll upload some sample questions for the exams. Glad you guys are finally asking some questions. Anything else? Does Anaconda take care of installation of Python? So yeah, Anaconda is sort of the way that I recommend installing Python. It is you download Anaconda, and then that will install a whole bunch of Python packages on your computer. And then later in the course, if we're doing a lab and you find that you need to install another package that's not a standard one, then Anaconda helps you do that and make sure that the version that you install is sort of consistent with all the other versions of software Python that are already installed. Okay, great questions. Any other questions? Okay. Well, if you guys think of more questions, you can ask me at the end of lecture. So let me move on then to the second set of notes. What is machine learning? And my goal here is just to kind of give you a flavor of what we'll be talking about technically in this course. So machine learning is really, quite a big world. We're going to be focusing on a few basic tasks. regression, classification, clustering, and compression. So I'll go through each one in turn and give you a flavor of what we mean for that particular task. And by the way, these tasks, even though the course is called like machine learning for ECE, it's really not at all specific to ECE. Machine learning is very generic and it's broadly applicable to engineering, science, medicine, business, and the tools that you learn for machine learning are quite general in any machine learning course. It allows you to basically attack problems from any discipline just from the data alone. That's the goal, is that you actually don't need to know anything, or let's say minimal about the application itself. Just you look at the data, and if you're good handling the data, then it's kind of universal. Okay, so let's talk about the first task, regression, or in layman's terms, predicting numbers. And let me just give you one example. Let's say we would like to predict tomorrow's stock price for some particular stock. And so maybe a traditional approach, maybe what people were doing, a number of decades ago, is that there would be experts on economics and whatnot in business, and they would have either in their head or written down some sort of models about how all this works, and they would consult their models, and they might plug in some numbers into those models, and that would give them, some prediction of what's going to happen with the stock. But it doesn't really work that well because the stock market is so adaptive, and it's really just fundamentally difficult thing to predict is a stock price. And so so an approach that's maybe more successful is to try to learn a model, given a bunch of examples of past data. Maybe we can learn about how trends occur, and then when we spot those trends, we can exploit them for prediction. Okay, so now the other thing about specific to regression is that the thing we're predicting is going to be a number, a numerical value. And essentially, in sort of the generic form of it, we want to estimate or predict some numerical value given measurements or data on other numerical values. And it doesn't have to be the stock market, it could be really just anything at all. So that's what regression is. What questions do you guys have on regression? Anything? Okay, we'll be, of course, diving quite deeply into a lot more details, but I'm happy to answer any high-level questions you have now. Okay, another kind of prediction task you can do is called classification. And the difference between regression and classification is that in regression, we're trying to predict numerical quantities, whereas in classification, we're trying to predict categories. And categories are things that are just not numerical, they're categories. So for example, maybe we want to predict a handwritten digit. And even though these handwritten digits are, we think of them as numbers like 0, 1, 2, and so on, really what we're trying to predict is we're trying to recognize if you see this image, then what category does that correspond to? If you see this image, what category does that correspond to? And what's challenging in this application is that it's really difficult to come up with a mathematical model of, say, like, what is the number 4? Because people write 4s in a lot of different ways. These are all 4s. And yes, there is something about them that I think we can recognize. And, we were taught in school, here's how you write a 4, but there's still quite a lot of variability. And as humans, we've just gotten very good at recognizing what a 4 is when it's written. Although sometimes it's very difficult. Maybe we can't tell whether something is a 4 or 9 or something else. So it's it's something it's difficult to come up with a mathematical model of a 4, but it's something that humans have learned to do. And so we might think, is it possible then to train a computer to do that sort of learning task where it sees this little image and then it says, I believe this is a 4. So that's like just one example is handwritten digits, but more generally, we're trying to estimate some category given some measurements of related quantities. It could be images, or it could be something completely different from images. So this is category classification. questions you guys have on classification. All right.
So how would the computer recognize the four? Does it use like polygons to detect the shape?
That's a great question. That's what we're going to be learning about in this course. There's really many, many ways you could try to do it. But yeah, we won't be using any or learning about any methods that use polygons. But it's a great question. Yeah, that's exactly the kind of stuff we'll be learning about, like all different options to do that. Yeah, that's what's going to be in the course. Any other questions? Okay. All right. So these two category or these two tasks we've talked about, they're both known as supervised machine learning because what you need in order to the sort of training data or even test data that you need for these models is you need examples of inputs and outputs. You need to know, like, I have a bunch of these images, and I know that all those are labeled as 4, and I have a bunch of these images, and I know that all those are labeled as 2. And then the task is, given one of the inputs, I try to predict the output label, the output category. There's some other tasks in machine learning that are not supervised. They're called unsupervised. In this case, there's really not examples of input and output. There's just examples of input. And so one of those tasks is called clustering. And let me just give you an example of clustering. Let's say you're given a bunch of collection of text documents, and you want to categorize these documents, but you really don't, you don't really know what's there. Maybe there's some documents on sports or science, or it could be anything. You have just no idea. So the whole goal is to try to do that categorization just from what you're given alone. And more generally, you're given a data set, and you would like to partition that data set into subsets so that the data is similar within each subset, but it differs across subsets. So here's another example of if your data are just pairs of numbers, we call them x1 and x2. And so each one of those pairs I can represent as a point on a plane where I have x1 on the x-axis and x2 on the y-axis. And here you can see if I gave you a list of pairs and I plotted them like this, you might say, oh yeah, I can kind of see the pattern here. Like this would be one cluster, this would be another cluster, this is another one, and this is another one. So that is an example, very simple example of what we're trying to do in clustering. Now, of course, there's all kinds of different ways you could do this that might give you different answers. And so we'll be learning about some of the most popular ways to do clustering. Any questions on clustering? Okay, great. So another task is compression or squeezing data. So maybe in this task, this is another unsupervised task. What we're given is a whole bunch of a big set of images. And the typical way that images are represented in their kind of most raw form is that it's sort of like a table of pixel values. Each one of these pixel values, if it's a color image, each pixel is really 3 numbers, typically red, green, and blue intensities. And if I give you a whole bunch of these images and I say, I would like you to represent them using less numbers than having to have a red, green, and blue value for each pixel, is there a way of doing that? And as we know, yes, there definitely are ways of doing that. There's very standard ways, like JPEG is, very common form of image compression, developed in the 1980s. And JPEG is sort of based on a number of ideas about how our brains perceive patterns. Also, it involves some information theoretic ideas about lossless compression and so on. And all those are put together, and it works pretty well. But it's still not optimal in any sense. And it's very generic JPEG. It's supposed to work pretty well on a wide range of natural images. But if I give you, let's say, a collection of just images that are all images of plants, you might say, well, that's like more specific than just generic natural images. Maybe I just knowing that they're all plants, maybe I can somehow squeeze that data even more strongly to, represent it using even fewer numbers. And so that would be the goal of machine learning. Can I learn a way of representing this data very compactly just based on the data itself? And another word or another phrase for this is called dimensionality reduction. So that's also another task we'll learn about. Okay, any questions about compression? Okay. All right, so that's just sort of like high level examples of the sort of things we'll be talking about. Now let's get a little deeper into how we might actually go about solving these problems. So as I mentioned before, the traditional approach that we might have been popular decades ago is you want to do something, you talk to a scientific expert. That expert has some equations or models that were posed by other experts, and they say, well, in this case, this is how things work, and so this is how you should solve your problem. And a great example of this in ECE is circuit design, right? Because we have things like Ohm's law. We have like very good equations that really do describe how things work, at least for, once you get to like super high frequencies or extreme situations, some of those equations break down. But for most of our circuit design tasks, like we understand the physics. And in many cases, that is exactly what you want to do. You just want to use those equations. You want to use that expert knowledge. But that doesn't always work. So one example we saw is that there's applications for which we do not have good models, like predicting the stock market. We don't really have very accurate models of how stocks evolve. So that might be one reason that the traditional approach fails, and we have to use some sort of learned approach. Another example would be maybe we do have a good scientific model, like say for acoustics, we understand acoustics very well. But in order to apply that model, we might have to know a lot of parameters that are simply difficult to estimate. So if we were in the regular lecture hall and I was lecturing and there was some sort of echoes in the room and those echoes were preventing you from understanding what I was saying, and you wanted to do some sort of echo cancellation, the acoustics are maybe pretty straightforward in terms of the equations, but in order to really apply those equations, you need to know a lot of details on exactly the shape of the room, the coefficient of absorption of all the different surfaces, including all the people in the room, where all those people are located, and so on and so on. So there's really just so many things you have to know in order to apply the theory, and it becomes impossible to do it that way. So instead, there's other methods that are learned or adaptive approaches. So things like, what happens in your noise canceling headphones. They're not working on any model of the room around you. They're just working on learning to try to remove noise and interference. Okay, so that's going to be the learning approach that we're going to focus on this term. And the main idea is we want to learn a model based on seeing many examples of data. Okay, so there's a number of key ingredients in doing this. So we need to have a modeling function. This function might be like the thing that predicts that stock price. It takes in some data we're using to predict the stock price, and it does that prediction. And this model is going to be, in many cases, a sort of generic model that has a lot of adjustable parameters. We'll call those parameters theta, and we'll say that there's D of them and they're all real numbers. Okay, now in order to adjust theta, in order to find a good set of values for theta, we need to have something called a loss function. And the loss function is how we're going to evaluate how well that model is performing. the smaller the loss, the better the performance. Now, in addition to that, we need some data on which to try out our model and evaluate our loss. So that's going to be our training data set. We would, in most cases, want that data set to be as large as possible for reasons that we will understand in a few weeks. Now, if you have the data and the loss in the model, you still need a way of adjusting those parameters because there's probably going to be way too many parameters for you to adjust manually. So you're going to need some sort of optimization algorithm. And it's going to try to adjust those parameters to make the loss small when evaluated on the training data set. So really, those are the key ingredients of machine learning, those pieces. And at the end of the day, the goal is we take that training data and we try to learn a model, an F theta, that works well, not only on the training data that we've seen, but on unseen test data. In some cases, it's very easy to get the model to work perfectly on the training data, but that does not mean it's going to work well on data that it hasn't seen before. So in order to get our objective solved, we're going to have to carefully design the modeling function, the loss, and the optimization algorithm. All those things matter. Any questions so far? Okay, so let me give you an example of how we can put these things together. And there's a lot of math on this page. If it doesn't make sense, don't worry about it at all. This is just a preview of something that by the end of the course, hopefully, if you looked at this page, it would be like, yeah, obviously that's how we do it. But at this point, if it doesn't make sense, that's fine. But let me just go for it anyway. So let's say the thing that we're trying to predict is this stock price Y, and this will just be a real number. And let's say that the data that we have to predict it, somehow we can summarize that as a vector of D numbers. And we'll call that vector boldface X. And so we want a modeling function, f of theta, that takes X as input and then outputs an accurate estimate of Y. And so one way to build that modeling function could be a deep neural network. There's a lot of other simple ways that we'll start with. Now, once we have that modeling function, we need a loss function that essentially tells us how well our modeling function is working. So if I write Y hat as my estimate or guess of Y, given the vector X and the modeling function, one way to build a loss would be to say, let me just take the difference between the true Y and my predicted Y and square that difference. And that's going to give me a non-negative number. The smaller that number is, the better, right? The closer my prediction is to the truth. That's not the only option. You could also take, just for example, the absolute value. We'll be talking about all these different choices later in the term. And this is what it's going to do. This is what the model is going to do for a particular X and trying to match a particular Y. But really, in order to train this F that involves many, many parameters, we need a whole bunch of examples. So our data set is going to look like a set of pairs of XYs, and we're going to label each one of those pairs with the subscript I. So X1, Y1 is the first example, X2, Y2 is the second example, and so on. In total, there will be N different examples, hopefully many, maybe millions. And this is the data that we're going to be using to figure out the status for our model. And putting all this together, this is sort of what we want to do down here, is if I think about a particular input Xi, I put that through my model, I get a particular output Y hat I. I compare that to the true Yi using my loss. We said we want this to be small. And for every I, for every training example, this is going to be of a certain size. Here, we're looking at the average across all training examples. Now that gives me a single number. And I want to make that number as small as possible. And I'm going to do that by adjusting the theta. Theta is a maybe big vector of parameters. I'm going to be adjusting all these parameters simultaneously to try to minimize this overall average loss on the training data. And this notation argmin, so if it was if I didn't have the arg, what this would mean is it would mean find the smallest value of the loss and return that number. But we're actually interested not in that number, we're actually interested in the thetas that achieve that. So this is the minimizer. Not the minimum, but the minimizer of the loss. And so it's that theta vector, the theta vector that minimizes this. We can call that theta hat. And now finally, I plug that into my model and I get f at theta hat. And hopefully that's going to be good for predicting unknown y later, given some vector of inputs x. Okay, so again, if this is a lot of math, don't worry about it. This is sort of an example of how we'll be looking at problems, and we'll be digging into all these different steps along the way. Any questions on this page? Okay. So let's, okay, okay, in particular, what are we going to learn? So for this modeling function, we'll be learning many different ways of doing that. We'll be starting with the simplest case of linear models. We'll talk about polynomial models, talk about neural nets, talk about decision trees. And for this loss function, we'll talk about important concepts like maximum likelihood, maximum a posteriori. We'll talk about kernel methods. In terms of how to optimize the parameters theta, we'll be talking about gradient descent, stochastic gradient descent, adaptive step size approaches like Miho's approach. And we'll be applying all these ideas to these tasks that we talked about earlier: regression, classification, clustering, dimensionality reduction. For each one, how do we build F? How do we build the loss? How do we optimize theta? And as part of all this, we're going to learn about important concepts like generalization, regularization, ensembling, principal components analysis, non-negative matrix factorization, Gaussian mixture models, expectation maximization, just a bunch of stuff. So that, yeah. So again, the main things we'll be learning are concepts in math, number one, but also standard software tools. Each of them on their own is important, but not sufficient. So if you just learn a whole bunch of math and you can't actually put this stuff into practice, it's not very useful. On the other hand, if you learn how to use a bunch of these software tools and now they're very capable, you can do a lot with them, but you really don't know what you're doing, you're again quite limited in the results you can obtain. So it's really critical to have both of these pieces, and that's what we'll be doing in this course. And again, we'll be assuming undergrad level linear algebra, statistics, and scientific coding. And linear algebra is going to be super important. I'm going to spend Wednesday's lecture going through just the things we need for this course. And then you'll have homework number one and a quiz and the first exam Friday in a week. All right. So that finishes what I was planning to lecture on today. What questions do you guys have on this stuff? Can you explain again the argument? Yeah, so I'll explain the argument in a picture. So if I have a function like this, and let me just say, let's consider theta as a real number. So if I said, what is the minimum value? This function, this is my f of theta. And we said, what's the minimum of f? That would be this thing. This is the min value of f theta. But if I said, what is the minimizer? This is that. This is the arg min f theta. So hopefully that makes it more clear. We'll be seeing this again, so you'll have plenty of chances to observe it. What other questions you guys have? Okay. Well, if there's no questions, but some of you have individual things you would like to ask me about or tell me about, I'll stay on the Zoom for now, and I will stop the recording. And but if not, we'll see you guys on Wednesday.